Welcome to the video on stoichiometry. Recall from a previous chapter that we learned about the mole and Avogadro's number. So if we review that topic quickly, the mole is a basic counting unit in chemistry. The actual definition: a mole of a substance is that amount of a substance that has the same number of atoms as exactly 12 grams of the isotope of carbon-12. An amount of any substance that contains 6.022 times 10 to the 23rd entities. That can be molecules, atoms, particles, ions, etc. So 1 mole is equal to 6.022 times 10 to the 23rd entities, just like a dozen is 12. 6.0221367 times 10 to the 23rd is Avogadro's number. Na is Avogadro's number. For example, if I have 1 mole of water, H2O, that means that I have 2 moles of hydrogen and 1 mole of oxygen. If I have 1 mole of ammonia, that means that I have 1 mole of nitrogen and 3 moles of hydrogen. And this is because of the subscript. So it seems like it's been a little while since we worked on these problems. So let's go ahead and see if we can solve a couple of these example problems to just refresh our memory. We're going to be going back to using dimensional analysis. And here we are given 2.75 moles of a sample of potassium. How many grams do we have in that sample? So remember, we're going to write over here that we're looking for grams. And over here, what we are given is 2.75 moles of potassium. The value that we know is the molar mass. Molar mass is the conversion factor we will use to go from grams to moles or from moles to grams. We want to put moles on the bottom, so we want moles of potassium on the bottom, and then we want grams of potassium on the top. And so the thing that we know is the molar mass, and if we look at the periodic table, the molar mass of potassium is 39.0983 grams, and that all is in 1 mole. The units, moles, cancel, and we're left with grams. And so if we do the math out, we end up with 107.5 grams, or with significant figures, 108 grams, and that's the final answer. Now the second example here, it wants to know how many sulfur atoms. So we're looking for atoms of sulfur and 5.4 grams of H2S. So we start with 5.4 grams of H2S. And so the first thing I'm going to do is go to moles from grams. So grams of H2S is going to be on the bottom. So my units cancel, and then we're going to have moles on the top, moles of H2S. So for every 1 mole of H2S, if we look up the molecular weight of sulfur and 2 hydrogens on the periodic table, that comes to 34.0808 grams in 1 mole. The next step is to get from moles of H2S to moles of sulfur, so that we're working towards what we're looking for. So if I put moles of H2S on the bottom and moles of S on the top, for every mole of H2S, there's just 1 S. So it's going to be 1 to 1. And so I know that moles of sulfur is going to go on the bottom. What do I have as a conversion factor that goes from moles of sulfur to atoms of sulfur? And if you're thinking Avogadro's number, you're absolutely right. So I'm going to put 6.022 times 10 to the 23rd atoms of sulfur in every 1 mole of sulfur. And so now grams of H2S cancels, moles of H2S cancels, moles of sulfur cancels, and we are left with atoms of sulfur. And if we do that math out, we get 9.5 times 10 to the 22nd atoms of sulfur, and that's my final answer. So here is some examples from the previous chapter where we went from atoms to moles, where we went from moles to grams, where we went from grams to moles to atoms, grams to moles to molecules, grams to moles to molecules to atoms. So you can see that we did do a lot of this work previously. So hopefully some of that will be coming back as we move through this chapter. So you might be thinking, okay, so what's new? So we already know all that. We already learned all that. What we're going to introduce in this chapter is the idea of using the balanced chemical reaction as part of our conversion factor. And so let me show you how we do that. If we have a chemical reaction between hydrogen gas and oxygen gas to make water, liquid, so in the balanced chemical equation, you see that we have 2 hydrogen molecules reacting with 1 oxygen molecule, giving us 2 water molecules. We're going to use those coefficients in the balanced chemical reaction as conversion factors, and let me show you what that means. So if we're talking about taking nitrogen, reacting it with hydrogen, giving us ammonia, in the balanced chemical reaction, we have 1 molecule of nitrogen combines with 3 molecules of hydrogen, giving us 2 molecules of ammonia. If we look at the table below, in terms of molecules, we have 1 N2, 3 H2, and 2 NH3. If we switch gears for a second and talk about the number of moles of each of these things, it is 1, 3, and 2. And finally, if we talk about the mass of N2 is 28.014, the mass of H2 is 2.016 grams per mole, and the mass of ammonia is 17.031 grams per mole. And so that's the molar mass of each individual molecule. So how do you think we can relate the number of moles in the balanced equation to the number of grams, either the starting materials or the products? What happens is we use the molar mass to convert the grams to moles from our starting materials, and then we do our mole to mole conversion based on the balanced chemical equation, and then moles to grams of the product. And I think this will make more sense as we do some practice problems. The mole method lets us know that the coefficients, the stoichiometric coefficients in a balanced chemical reaction are the number of moles of each substance. So we're going to call that our mole to mole ratio. And the bottom line, and you're going to hear me say this over and over again, if we are given mass in grams of A, we can go to moles of A using the molar mass, and then using our balanced chemical equation up here, using the number of moles here, we can then convert from moles of substance A to moles of substance B. And then we can use the molar mass to go back to mass of B. I think this will make more sense as we start doing practice problems. You're going to hear me say a bunch of times, if you start the problem in grams, you're going to go grams to moles, and then you're going to go mole to mole, and then you're going to go moles to grams. And so that's a regular trend in many of these problems. And I just want to highlight for 1 second, the bottom line is you always have to have a balanced chemical equation first. You cannot start this stoichiometry without a balanced chemical reaction. We've talked about the fact that when we're solving these dimensional analysis problems, we are given some value and then we are looking for some value, right? And I even have you write it on the paper. Here's what we know over here on the left, and here's what we're looking for over here on the right. And then you're given some value. So your known thing starts on the left. If you are given particles, so molecules, atoms, ions, any of those particles, and we need to go to moles, we are going to use Avogadro's number for that conversion. If we are given mass, we are going to use the molecular weight or the molar mass to get to moles. And something new in this chapter, if we are given volume, we are going to use the conversion that for every 1 mole, we have 22.4 liters. And so that's our conversion. If we are given volume, we are going to use 22.4 liters per mole as our conversion. So we can get to moles from particles using Avogadro's number, from mass using molar mass, and from volume using 22.4 liters per mole. Once we have moles of one substance, we are going to use the balanced chemical equation or the mole to mole ratio to go from moles of our known to moles of our unknown. And so once we have moles of our unknown, we can move forward and solve for particles using Avogadro's number. We can solve for mass using molar mass, and we can solve for volume using 22.4 liters as our conversion. So again, I just want to reiterate, we can start with particles, mass, or volume. We go 2 moles. We use our mole to mole conversion, and then we have moles of another substance. And from there, then we can go to particles, mass, or volume. There's more details than I gave because in each of the boxes, it tells us whether we have to divide or multiply by our molar mass, Avogadro's number, or 22.4. You can peek at that as well. And so what I want to do first, like I promised, is show you some examples. So the question is, how many grams of N2 are needed to completely react with 21.2 grams of hydrogen to form NH3? So the first thing we need is a balanced equation. So this word problem tells us that we are going to be reacting N2 with H2 to give us NH3. And so if we work on balancing this equation, right now we have 2 nitrogens and there's only 1 nitrogen here. So the first thing I'll do is put a 2 here. And so now we have 2 nitrogens and 2 nitrogens. And now hydrogens on this side. On the product side, we have 6. We're going to need to put a 3 here. And then we don't need to put the 1 in, but you could. So there's just 1 nitrogen. So the balanced chemical equation is N2 plus 3H2 gives us 2NH3. So now that we have the balanced chemical equation, we can start solving the problem. What we are given in this problem is 21.2 grams of H2. And what we are solving for is grams of N2. Question says, how many grams of N2 are needed to completely react with the H2? Okay, so if we're given grams, the first step is to go to moles. And so we know we're going to use the molar mass, and we want grams of H2 on the bottom, so it cancels. Moles of H2 on the top. So if we look at the molar mass of H2, calculate that out, it comes to 2.0158 grams in 1 mole. And so now my grams is canceled. And so now I'm converting from moles of H2 to moles of N2. So we want moles of H2 on the bottom and moles of N2 on the top. And if we look at our balanced chemical equation, this one has a 1, this one has a 3. And so for every 1 mole of N2, we have 3 moles of H2. And so now we are at moles of N2. And now to get to grams of N2, we're going to use molar mass. Now we need moles of N2 on the bottom here, so it cancels, and grams of N2 on the top. So if we add 2 nitrogens together, we end up with 28.0134 grams of N2 in every 1 mole of N2. If we cancel out our units, grams of H2 cancel, moles of H2 cancel, moles of N2 cancel, and we are left with grams of N2, which is exactly what we're looking for. If we do this math out, we end up getting 98.2 grams of N2. So if I quickly recap what I did, we had mass, we used molar mass to get to mole, and then we used our mole to mole ratio from the balanced chemical equation to get from hydrogen to nitrogen, and then we used molar mass to get back to grams. If I do the second example for you, aluminum reacts with chlorine gas to form aluminum chloride. How many grams of aluminum chloride can be produced from 2.8 grams of aluminum and excess chlorine gas? So if we're going to write our balanced chemical equation, this says aluminum, so that's going to be aluminum solid, plus chlorine gas, and chlorine is a diatomic, so it's Cl2, goes to aluminum chloride. So remember, aluminum is +3 and chlorine is -1. So if we do the crisscross, it's going to be AlCl3, and that actually is also a solid. You don't need to worry about phases in this part of the course. If you have them, use them, great, but you don't need them. Now, if we're going to balance this chemical equation, which is the next step, so aluminum, we have 1 on each side. That's great. But okay, so the chlorine here is 3 and the chlorine here is 2. In order to balance this, we're going to make that 6 on both sides. This is going to have to be 3 Cls and 2 AlCl3s, which means that we also need a 2 here. That should be balanced. And so there is our balanced chemical reaction. So now dimensional analysis. The question is asking us how many grams of aluminum chloride, so we want to solve for grams of aluminum chloride, can be produced from 2.8 grams of aluminum. So we're given 2.8 grams of aluminum. aluminum. So the excess chlorine gas just means that that's not going to limit us, but we have to start with and work with 2.8 grams of aluminum. And so if we have grams of aluminum, we're going to take that to moles using the molar mass. We're going to put grams of aluminum on the bottom and moles of aluminum on the top. And we know that the molar mass from the periodic table is 26.982 grams of aluminum for 1 mole of aluminum. Now the grams of aluminum cancel, and we have moles of aluminum on the top. So now in order to do the mole to mole ratio, we're going to do moles of aluminum on the bottom, and then we want moles of aluminum chloride on the top. We're given aluminum and we want to go to aluminum chloride. So that's what we want on the top is aluminum chloride. And if we look at the balanced chemical equation, we have 2 moles of aluminum for every 2 moles of AlCl3. 2 moles of aluminum for every 2 moles of AlCl3. Now, to get back to grams of AlCl3, we're going to put moles of aluminum chloride on the bottom, and we're going to do grams of aluminum chloride on the top. And if we add up the mass of AlCl3, 239.7 grams of aluminum chloride, and if I do that math out, I come up with a value of 25 grams of aluminum chloride. And that's the final answer. Again, we have the number and the units. And in this case, we need the actual compound as well. Here's a practice page that we will work on together in class. If you wanted to start thinking about it before class, that's great. You want to be careful because sometimes I'll give you the balanced chemical equation. Other times it won't be balanced. Before we do anything, we always have to make sure that we have a balanced chemical reaction. That's the bottom line for this chapter. Balanced chemical reaction before we do anything else. Now, if we take this concept just a little farther, we'll start talking about limiting reagents and percent yields. Let's go. Limiting reagent. And if we think about making some s'mores sandwiches over an open fire, for each s'more, we're going to need 2 graham crackers, 1 marshmallow, and 3 pieces of chocolate candy. And if what you are given is limited to right here, we see that we're probably going to run out of either the graham crackers or the chocolate first, right? We have plenty of marshmallows. So in this case, the marshmallows would be our excess reagent. If we look at the number of graham crackers, here's 1 sandwich, 2 sandwiches, 3 sandwiches, 4 sandwiches is all we can make in terms of the graham crackers. And in terms of the chocolate, it looks like we have maybe 1 here, 1 here, 1 here, 1 here. So that one also can only make 4. The chocolate and or the graham crackers would be what's called our limiting reagent. During a chemical reaction, just like in making of s'mores, we may run out of one of the reagents before the others are completely reacted. So that brings us to the idea of our limiting reagent. It's the reagent that gets used up first in a chemical reaction. And excess reagents are the things that are actually in greater quantity, and so there's extra of those. Whichever reactant gives you the lesser amount of product is the limiting reagent. So we can go back and solve the problems that we've been solving all along, and we can determine how much we would make in the product. And if we solve it for each of the quantities of the reagents that we're given, then ultimately one of them is going to probably be limiting. And then that's the one that gives us the answer to how much can be made. If here is our practice problem, the overall chemical equation looks like magnesium solid plus nitrogen gas gives us Mg3N2 solid. So there's our chemical reaction. The next thing we have to do is balance our chemical reaction. If we look at the magnesium, it looks like we need to add a 3 here. We have 2 nitrogens, and so that stays as 1 and that stays as 1. And so I'll write those both in. And so there's our balanced chemical reaction. And so now the problem asks, how many grams of product, Mg3N2, how many grams of product is formed if we start with 45.00 grams of magnesium, or if we start with 20 grams of nitrogen. And so now we solve both of these dimensional analysis problems and figure out which reagent gives us the smallest amount of product, which means that's the limiting reagent. And that's the answer. And whichever one over here comes out to be the smallest number is our winner. And so we will finish this problem in class. The next thing I want to talk about is percent yield. In the lab, when we go and do a chemical reaction where we mix two reagents together, heat it, stir it, wait for the reaction to go to completion, very often every single molecule of our starting material does not actually go to product. Why? Because sometimes the reagents just don't react that way and they are left over and they just don't react. Other times we may have a side product, so some other thing that's formed besides the desired main product that we want. Or potentially we could lose products when we're purifying or collecting. And so there's lots of different ways that we can lose product. Very rarely do we ever get 100% of our starting materials to convert to product where we can actually collect it. So therefore, we're going to have to talk about a couple different terms here. One is going to be our theoretical yield. Our theoretical yield is the yield that we would get if every single molecule of our starting materials reacted, depending on the limiting reagent. Every single molecule of our limiting reagent reacted and went to product and we were able to get it. That would be 100%. So what we will do is we will calculate that theoretical yield. In an ideal world, how much could we get based on our limiting reagent? So we'll do that calculation and that's straightforward. The second thing is the actual yield. Now the actual yield you can't calculate. The actual yield is determined in the laboratory. So we do the experiment, we get our product, and we weigh the final product. And so that's going to be our actual yield. That's determined experimentally. You cannot calculate that. We have to get it from the lab. The way we figure out our percent yield is to take the actual yield that was determined experimentally in the lab and divide it by the theoretical yield, which is the one we calculated based on the limiting reagent, and multiply by 100. So actual over theoretical times 100 is the way we will determine percent yield. And there are a couple practice problems on this calculation as well. Okay, see you in class.